Hello friends, welcome back. In this video, we are going to study the multiple bonding. Multiple bonding, that is the d-pi p-pi and the d-pi d-pi type of bonding. So let's start with the multiple bonding. So according to the valence bond theory, each ligand must contain at least one lone pair of electrons to form a sigma bond, right? There is a donation of electrons from the ligand to metal and it forms a sigma bond. There are many ligands such as the carbonyl or the CO ligand, RNC ligand, PX3, PR3, ASR3, SR2, etc. So these are the various types of the ligands which are poor electron donor. Still they are forming the many stable metallic complexes, right? So Pauling supposed that atoms of the transition metals are capable of forming the multiple bonds. Means in addition to sigma bond, they should form the pi bonds. That is the multiple bonds. So here we can say that in addition to sigma bond, pi bond may be formed between the metal and the ligand, right? So in this case, electrons are donated by the metal to the ligands to form the pi bond, and which is called as the back bonding. Generally we say that the electrons, they are donated from the ligands to metal, which is forming the sigma bond, in which ligands, they are having the filled orbitals and metals, they are having the empty orbitals. But in the opposite case, the metals, they are having the filled orbitals and the ligands, they are having the empty atomic orbitals. So the electrons, they are donated from the metal to ligands. That's why they are forming the pi bond, and that is called as the back bonding. So there are two types of pi bonding found in complexes. The first one is d-pi p-pi bonding. That means the bond is formed between the d orbital of metal and the p orbital of the ligand. And the second one is the d-pi d-pi bonding, in which the pi bond is formed between the d orbital of metal and the d orbital of the ligands. So let's study these two types of the pi bonding. So we are having the first one, that is the d-pi p-pi bonding. So again we can say that there is a formation of pi bond between the d orbital of metal and the p orbital of the ligand. So how the pi bond is formed? The pi bond is formed due to the lateral or the sidewise overlapping of the atomic orbitals. So the donation of electrons from metal d orbitals, the metal d orbitals such as the dxy, dxz, dyz, to the empty p orbitals of the ligand form a bonding which is known as the d-pi p-pi bonding, right? So the electrons, they are donated from the metal d orbital, which are the filled metal d orbitals, to the empty p orbitals. So that's why it is called as a d-pi p-pi bonding. It is commonly observed in the complexes with the ligands like CO, CN, etc. So the complexes which are having the ligands such as the carbonyl ligands, cyanide ligands, they shows the formation of the d-pi p-pi, because these ligands, they are providing the p atomic orbital and the metals, they are providing the d atomic orbital. For example, nickel tetracarbonyl, right? Nickel, it is a metal which is having the d atomic orbital, and carbonyl, the carbon is using the p atomic orbital, right? Or this type of bonding occurs when the ligands contain an atom from the second row of the periodic table. So the ligand specially contains the atom from the second row of the periodic table, then also they form the d-pi p-pi bonding. For example, the nitrogen in the ligand NO2 minus, then carbon in the ligand carbonyl, carbon in the ligand cyanide. When these are present as a ligand, they gives the formation of the d-pi p-pi bond. Let's take an example such as NiCO4, that is a nickel tetracarbonyl. Now in this nickel tetracarbonyl, this nickel is attached to the 4 carbonyls, right? Let's draw the structure for this. So we are having the nickel that is the metal which is having the d orbital, and then we are having the carbonyl which is the ligand which is providing the p atomic orbital. So metal d orbital and the ligand p orbital, they undergo overlapping, which is the lateral or the sidewise overlapping, and due to this lateral or the sidewise overlapping there is a formation of the bond which is called as the pi bond. Okay, so in this NiCO4, we are having the lateral or the sidewise overlapping to give the formation of the pi bond between the d orbital of the metal and the p orbital of the ligand. That's why it gives the formation of the d pi p pi bonding. Now in carbonyl, one of the p orbital is empty, and hence it is filled in the lateral or the sidewise overlapping with the metal d orbital to give the formation of the d pi p pi bond. Okay. Then the second type of bonding is the d pi bonding. In short, we can say that there is a overlapping of a d orbital of metal and the d orbital of the ligand. There is a lateral or the sidewise overlapping which gives the formation of the pi bond. Now here in this case, the metal d orbital is filled and the ligand d orbital is empty. That's why the electrons, they are donated from metal to ligand. Hence it is called as the back bonding, which gives the formation of the pi bond. So donation of electrons from the metal d orbitals such as dxy, dxz, dyz to the empty d orbitals of the ligand forms a bonding which is known as the d pi bonding, right? Now it occurs when the ligands contain an atom from the third or the latter row of the periodic table, such as the elements phosphorus, sulfur, etc. For example, its example is M double bond px3. M is the metal which is attached to the ligand px3. So let's draw the structure for this. We are having the metal d orbital, right, and the phosphorus which is from the ligand. So metal d orbital and the ligand d orbital, they undergo overlapping like this. They undergo lateral or the sidewise overlapping, and due to which we are getting the formation of the pi bond, and the bond is the d pi bonding. So this is the second type of bonding in which the pi bond is formed between the metal d orbital which is filled and the ligand d orbital which is empty, and hence it is a d pi bonding. Then let us see the limitations of the VBT or the valence bond theory. The first limitation is it gives only qualitative explanation regarding the properties such as bonding, structure and magnetic properties of the complexes. Then it fails to give any qualitative explanation of these properties. Only it gives a qualitative explanation. Then it cannot explain or interpret the spectra of complexes. The third limitation, it cannot explain why certain complexes are more labile than the others. The next one is it cannot explain the detailed magnetic properties of the complexes. Then in VBT, it is assumed that all the d orbitals are of equal energy. We know that there are 5 d orbitals and they are not a degenerate, they are splitted. But VBT shows that they all are of equal energy, but generally they are of different energy. It does not consider the splitting of d energy levels. Then it does not account for the relative energies of different structures. It fails to account for the observed geometries of certain complexes. Then it does not explain why the water or the H2O and halide ions commonly form high spin complexes while the cyanide or the Cn- forms the low spin complexes. There is no explanation given by this theory. Then it does not give any satisfactory reason for the formation of inner and outer orbital complexes. So thank you. So this is regarding the Pauling's valence bond theory. Thank you.